This video will show why we can't use a binary system to represent fractions exactly. If we start off with a number line, just got to get a number line up here. So we'll begin with that, and let's take a quick look at, say, 0, 1, 2. And not to scale, but if we had -1 over here, etc. Well, we can easily get these numbers in unsigned binary. For example, 2 would just be 0, 1, because it's 2 to the 1, 2 to the 0. And if we used a signed representation, such as a 2's complement, then we can show our negative integers. But what about this whole range in here? If we look at, say, 1 to 2, we need some kind of fractional representation. If we take where our denominators are powers of 2, for example 1/2, then we can express this as 2 to the -1. And if we wanted to say, well, what's a quarter? This is 1 over 4, which is 2 to the -2, because 4 is really just 2 squared. What happens if we want to go on this side and we want to get, say, 3/4? In order to get to 3/4, we have to take 1/2 plus 1/4, which will be in decimal format. So everything looks pretty good. We can get to some decimal numbers. We can represent them exactly. But the problem comes in where we want to represent numbers that we can't get to exactly. Let's look at 0.1. So for this section, we want to look at an extended number line. So we'll build a new number. Give ourselves a lot of space. And we'll go back at 0, 1, and I'll use decimal format here because it'll be easier to see. Break it up again. Now this would be, this was 1 over 2 to the -2, so here would be 1 over 2 to the -3. And run out of space there. Now these numbers are starting to get a little bit harder to see. We'll do one more and I'll show you how to calculate that. So here we would have to take 0.0625 divided by 2. We get 3,125. 2 times 2 is 4. You can subtract your 4, carry your 1 there, and then 10 divided by 2 would give us 5. If we wanted to get to 0.1, 0.1 is going to fall somewhere around here. Actually, let's go with a different color so you can see where we want to go better. So in the red, we want to go somewhere around here. But in order to get to there, we have to add these these fractional components in to get there. We can't start with 0.125. That's too large. 0.0625 is going to be too small, so we can try to add another part onto it. So if we add on this smaller part, we'll get 0.3125. We can always extend zeros past there. Add these together, and we get a number that's closer, but not exact. So maybe we need to add another portion. This is going to get really fine and hard to see. But this one there would be the same approach. If we divide by 2 here again, we get 0.01, carry the 1, 5, carry the 1, 6, 2, 5. Now you may need super glasses to see that, so we'll copy that down over here. 0, 1, 5, 6, 2, 5. So how about we add that small part? And we should be able to see right away. I don't have to add this because if we added just these two parts, that would give us 0.1, but we have this extra stuff past there. So I'd actually have to skip that one and look at further divisions of 2, and the numbers would get really tiny. If we zoom in on just the portion that we're interested in, so let's get back our, here's the 0.1 that we want. And if we use this approach and we keep adding on, here's our, that's when we add on our 0.03, and we add the next higher one, we can get as arbitrarily close as we want to 0.1 exactly, but we'll never be able to get exactly on to this particular line. We're limited by the number of bytes. As we extend the bytes, we can get closer to it, so we might be able to get, say, there, or even there on the other side. But somewhere, we'll have to estimate it. The number might look something like 0.100000000, whatever, 825, what other numbers work out to. And if we're going for a level of precision, say here or even here, then the rest of this would just be garbage afterwards. And if we're just using this for one number, one calculation, that's fine. But if we're multiplying this by a really large number, this garbage portion of the number may become relevant. It could be significant. And there have been cases, such as a rocket system, where they multiplied a number like this by a really large number, and the error that was caused by that with other calculations caused the system to fail. So the point of this is that there's some numbers that we can't represent exactly. So 0.01, let's make that a little bit more visible. Go with red. Cannot be represented exactly. When the denominators for in the fractional form are binary, those ones can. Or if they can be summed with denominators that are binary powers, those ones can. But not this one. If you want to read up more on how this works, then you would want to look at, it's a standard that's called IEEE 754, and it's talking about floating point notation. The term floating point comes in from how this decimal is represented and the format that they use for the different in the bytes to say which part belongs to what for the encoding. That's all for this video, but take a look at that if you want to learn more about this topic.